Lab 2, motion of a falling object. So the purpose of this lab is to observe the motion of an object that starts at a certain height and falls. The object must fall noticeably slower than a rock, which means it must be affected by air resistance. This lab will help students better understand how forces like gravity and drag affect an object's motion. So a quick preview of my results. My computational models showed that drag significantly affected the motion of the object in my video. While they weren't entirely the same, the position coordinates in my gravity and drag computational model are very similar to the coordinates in my tracker video, and the coordinates in my gravity-only computational model were pretty different from those in the other model and the tracker video. So the physics principles I used were Newton's second law, which states that the acceleration of an object is determined by the mass of the object and net force acting upon it. Formula's right here. Then I also used the force of gravity, which is F equals m times g. The drag formula, which is right here. The velocity formula, the position update formula, and the velocity update formula are all used in this lab. Okay, so here's my tracker data. I used a tissue box as my object. So the tissue box is the system, while everything else in the room are the surroundings. Here's my gravity-only model, in which gravity is the only force acting on the system. So you can see my code here. I've got my formula for the velocity, which is just updated by net force divided by mass times delta t. Same thing with position. It's not shown here, but my initial velocity vector is 0, 0, 0. My initial position vector is 0, negative 0.02, something small due to an error in the tracker video. And then my formulas for net force and drag are right here. And then here is my gravity and drag model, in which gravity and drag are acting on the system. Everything else is the same. The only thing that's different is that B is actually 0.5. B is equal to drag. So in the previous one it was equal to 0, while this one has drag, which can be attributed. It's where we can attribute the the differences in the graphs. So here's my graph with all my data. As you can see here, the two computational models start off pretty much the exact same, but end up diverging quite a bit. And the coordinates from my tracker video start off a little different than the models, but eventually kind of converges with my gravity and drag computational model. So those two are pretty similar in the end, and the gravity-only computational model is quite a bit different, as we can see here, which of course can be attributed to drag acting on the tissue box and causing it to not fall quite as quickly. So the possible sources of error for me in this lab are mainly just human errors. There could have been a slight error in placing the center of mass in each frame of my tracker video, and obviously there could have been errors, dropping it. There could have been, something could have been affected the motion. But mostly the errors are, pretty minor and won't affect the results of the lab too much. So the what does it mean question. So out of the two computational models, only the gravity and drag models predict only the gravity and drag model predicts a terminal velocity, and this can be explained by the presence of air resistance and drag, because eventually the force of drag will equal the force of gravity, causing the system to have a net force of 0 and reach terminal velocity. So, since the gravity-only model has no force of drag, the system will continue to increase in velocity and will never actually reach a terminal velocity. And then the what-if question, what if the object was thrown downward to start the experiment, meaning the initial velocity would not have been 0? So by examining the graphs and looking at velocity as a function of time, we can see that while the object thrown with a greater initial velocity, which is shown on the bottom graph, will end up reaching terminal velocity a little quicker, it does not actually change the terminal velocity. It's still the same, because the force of gravity and the force of drag, they're still the same. Thank you for your time.